Okay. First let's do some quick review. Okay. Review. Okay. We have S1, S2, to Sn. They are independent, identical distribution with the normal distribution with mean mu and variance sigma squared. Okay. And then we have following property. The first one is we know that the sample mean minus mu divided by the standard deviation and times the square root of n. Then this will also follow the normal distribution with mean needle and variance 1. Okay. And the second one is if we define the S squared, which is the sample variance, is 1 over n minus 1, summation from I equal to 1 to n, and Si minus S bar with power 2. Okay. Then the distribution of this n minus 1 S squared divided by sigma squared, and this will be follow the chi-square distribution with a degree of freedom n minus 1. Okay. And the next one is we want to know the distribution like this: square root of n sample mean of x minus mu divided by s. So in here we use the sample standard deviation rather than the population standard deviation. And in this case, this will follow distribution of t n minus 1 with a degree of freedom n minus 1. Okay. Okay, we can also do some calculation like this. We know if Z is a standard normal distribution, if it's divided by the chi-square n over n, and this will follow this distribution with degree of freedom n. Okay, and so we can do some thing like this. It will become the S bar minus mu divided by sigma, and the denominator will become like this: n minus 1 S squared sigma squared over n minus 1. Okay, so the numerator is z, and this one will be chi squared n minus 1. Then we can say this the whole thing will become the t distribution of n minus 1. Okay. Okay, and these properties are very useful for ways to where we have the distribution S1 to Sn are normal distribution. Yeah. Okay. So please remember these three properties. Okay, and then let's go to the problem. The first problem is when x is uniform on needle 1, and if condition on x, y is uniform on needle 2x. We want to find the joint and modular distribution of x and y, and we want to ask are x and y are independent. Okay. Okay, so the problem 1, we know x is uniform distribution, the 1, and the y condition on x is uniform needle x. Okay, so first let's find the joint distribution. Okay, the joint distribution of x and y is equal to y conditional x with the modular distribution of x. Okay, we know this one is 1 independent function from 0 to 1. Okay, and from the definition we know this is equal to 1 over x independent function y belonging to 0 to x. Okay, so the joint distribution would be like this: 1 over x indicator function, okay, y greater than 0, smaller than x, and indicator function x greater than 0, smaller than 1. Okay, the modular. Okay, the fx, the modular difference of fx is easy. From the definition we know is this one. However, if we want to know the modular distribution of y, we need to use this. We need to use the integral of the joint distribution x. Okay. So they can become like this: 1 over x indicator function 0 y x indicator function 0 x 1 dx. Okay. Okay. So now we study this, and you can see in this the x will be greater than y, and x are also smaller than 1. Okay. So the integral will be from y to 1 and 1 over x dx. Okay, and this, the integral of the 1 over x will be log, so it can be log x, and the domain is from y to 1, so it should be log 1 minus log y. So, and log 1 is 0, so it's negative log y. Okay, so this modular difference, and we can see that independent. So because fy, the product of modular distribution is not equal to the joint distribution. So that means y and x are not independent. Okay. Okay, and for question 2, the x is uniform distribution at -1 to 1, and y is x squared. We also want to find the joint and modular distributions of x and y, and also we want to find the covariance of x and y, and we want to ask whether x and y are independent. Okay. So, problem 2. So we have x is uniform, -1 to 1, and y is equal to x squared. Okay. This obviously that y is not independent to x because y is a function of x. But we can also do what we did before, like find a joint distribution f x and y. This equal to, okay, this one is tricky. 1 over 2 is 0. And when okay, so we know that y should be x squared. So here is x, and x should be -1 to 1, and y should be y is equal to x squared. Okay, so it's like this, and the orders will be 0. Okay. Okay. The marginal distribution. Also, the marginal distribution of x is easy. Is 1/2 indicator function x belong to -1 to 1. Okay. And the modular distribution of y should. Okay. In this case, I want to do the thing like this. Okay. We find the CDF first, and then we use the derivative of CDF to find the PDF. So I can define FYY like this. Okay, and this is equal to probability of x squared smaller than y. This is equal to negative square root of y x smaller than square root of 1. Okay. And this is equal to the integral from negative square root of y to square root of y, and x is 1/2 indicator function from -1. Okay. dx. Okay. So from the indicator function, we know that y should be from 0 to 1. Okay. So if y below the is not equal to 0 and 1, so how about okay, sorry, let's so in this case we can see, okay, first, if y is greater than 1, then the PDF, the CDF equal to 1. That is because x squared will be always smaller than 1, so it's 1. Okay. If y is below to 0 to 1, we can get rid of an indicator function. So in this case, this fyy is equal to this dx. So the answer is square root of y. Okay. And if y is smaller than 0, okay, you can see, because y is square root of x, so implies that fyy is equal to 0. Yeah, because y is the square root of x, and the square root of x is always positive, so the CDF of y when y is smaller than 0 is 0. Okay. Okay, so in this case we can know that we can find the derivative of fyy. Okay. B square root of y, which is 1/2 y with negative y to the negative 1/2. Okay. And this will be okay. So we can define the CDF like this, PDF like this. indicator function 0 to 1. Okay. Okay, so we have the joint distribution and the modular distribution. And also we need to find, so from this we can know fx, the product of the CDF, the modular distribution is not equal to the joint distribution. So implying it's not independent. Okay. And next thing, we want to find the covariance of x and y. This is equal to covariance the first mode x times first mode y minus the exponential of x and y. Okay. We know the average of x is equal to 0 because x is uniform from -1 to 1. And this one is equal to the third moment of x, which is also equal to 0. Okay, so we can see the covariance is equal to 0. Okay, so from this example, we know that if two random variables they are uncorrelated, so x and y are uncorrelated, it doesn't mean x and y are independent. Okay, so uncorrelated, the definition of uncorrelated is the covariance of x and y is equal to 0. But in this example, we can see they are not independent. But if x and y are uncorrelated, join Gaussian. Then x and y are dependent. Okay. So in here the important condition is they are joint Gaussian. So if x and y are joint Gaussian, uncorrelated can imply the independence. Okay, the problem 3. Okay, the problem 3 is we have two random variables x and y, and they have finite second moments, and we define a function MSE, which is the mean square error. Okay, as the expectation of x minus bx with power 2. Okay. Okay, and we want to find the beta square, which minimizes the function mean square error beta. Okay, and please write the beta star in terms of the moment of x and y. Okay. So that means we want to write the beta star as the function for this, or this, Okay. Okay, problem 3. The mean square error is equal beta is equal to this. Okay, beta x. Okay, so in this case we can do some algebra and we can get this. Beta square the second moment of x. Okay, so if we find the derivative of the mean square error and we find its solution, which would be the local maximum or minimum of this function. Okay, so in this case we find derivative, it would be 1 plus 2 beta second moment of x. So the solution of beta has, okay, I want to write it as beta star would become like this. The correlation of x and y divided by the second moment of x. Okay. Yeah. So this is the solution. Okay. But we have to check whether this one is the local minimum. So we have to do the second derivative again. So second derivative of this function then will become the 2 with this. Okay. And we know that this one is always positive. So this is positive. So that means the mean square error function is convex. So the solution of the first derivative is local minima. Okay. So the beta star is local minima. So we can get a solution. Okay. Okay, that's all.